Looks like I'm live. Uh, Hello, everyone. Welcome to the very first stream. In this series, I will solve Grind-75 problems. Link to Grind-75 will be posted in the description. Uh, I will be solving problems at the same time explaining my logic just like I would do in an actual interview. And so so what I have done is it's like in my linked in my lead code account. I have created I have created a list for all 75 problems from Grind 75, and we'll start solving them one by one. At any point, feel free to join my Discord server. Feel free, if you like this stream, like this format, or if you want to see something else, please like and subscribe, and please chime in on the chime in on Discord channel for any content requests. Uh, Without further ado, let's get started. So the very first problem in this list is two-sum problem. It's a classical problem. It's a classical first problem in many lists. Uh, Given an array of integers and an integer target, return indices of two numbers such that they add to target. And you may assume that there are certain assumptions, you may assume that each input would have exactly one solution and answer could be returned in any order. So, and now this assumption actually makes things a little simpler, uh, because we are going to assume that we have to assume that there is exactly one solution available. And okay, before I go any further, I'll be using Java for this slow run. If if there is request for any other languages, I will, as and when time permits. After this, we can start another slow run. Okay, so let's get started. This problem, it means now this numbers, there is no assumption that this numbers array would be would be sorted. So we can't exactly do something like this, something like a binary search for every individual value. But what like if we were to do like a brute force solution, that would be for every number in the array, we would have to search the array for target minus that number. And if target minus that if it doesn't exist, we simply move on to the next number. But this would require uh, one array walk for every number, maybe not the numbers which we have already seen, but for every index we would have to look for the numbers after the number all the numbers coming after that index. And that would be a quadratic time complexity solution. Instead, uh, instead, if again, this is a trade-off between memory and the compute time. So assuming we do not have any memory constraints, what if we could remember something and use that memory to help look up, maybe we can solve it. And that structure, and that's like the very basic structure called a hash map. Again, explanation of hash map, like again, in case we need any explanation, like if there is content request for explanation about hash map and hashing strategies, etc., please feel free to chime in on Discord or comments, and I'll prepare a slide deck as and when time permits. But right now, let's just describe the approach and solve this problem. The approach is simple. For every number, we first check if target minus number exists. We initialize a hash map which would contain numbers we have seen so far, mapped to and the value as keys, and mapped to their the index. Again, here we are not concerned about here we are not concerned about duplicate numbers, because the assumption is there is exactly one solution. So even if there are repeated numbers, like based on the assumptions, that would not matter, because that would not be a solution. Uh, so what we would use hash map is to store number and its index, map to its index, and if and while traversing the array, uh, when we encounter a number, we first check if target minus number is present in the key. If it is, then that index and the current index becomes our solution. Okay, so the way to code this is, and I now, since we are we need actual indices of the two numbers, we cannot use a for each loop, which is preferable in modern Java. So let's just use a good old-fashioned loop. So this is the way to look up if a key if a key exists in in a map. And since this seems to be repeated so much, let's just cache this. It doesn't make difference in execution time because JVM would anyway cache the JVM would anyway cache this value, uh, but it looks cleaner and more readable. Mm. Current current and candidates. And let's again we assume that solution exists, so which means that which also makes takes away some corner conditions, but we'll write the corner conditions nevertheless because that's what we would be doing in production code. And let's just cache this error response. Uh, I mean, throwing an illegal argument exception is also acceptable in this case. And let's see. Hmm, hmm. And of course, and let's check what happens. Okay, uh, so that takes care of this. And by the way, like without this last return statement, this won't compile because like even though assumption makes it explicit that there would be exactly one solution. That's not something compile. I mean that's an artifact of input rather than something we can tell the compiler. Okay, let's move on to the next problem. Given a string is containing just the characters, uh, again, braces, determine if the input string is valid. So now, again, we are not following mathematical rules where like which explicitly define how brackets are how brackets are supposed to be ordered. Square bracket, then then curly bracket, then normal parenthesis, and beyond that, bar brackets. That's the classical mathematical expression about bracket precedence. See, but this does not concern that. This still like here the order of brackets and like order of nesting brackets is not material. Now, if it were just a single type of brackets, we could potentially have just used a counter and like just passed over the string, counted open braces, closed braces, like added open braces, subtracted closed braces, and made sure that till the at the end of the string, uh, counter is zero, and at no point during the traversal counter becomes negative. That would mean a valid string. But here there are multiple types of braces, and that means some kind of memory we have to the memory needs to be maintained. Specifically, the last open brace is open brace, because every closing brace, as we traverse the string from start to end, every closing brace has to map to the last opening brace. And in order to do that, it's better to it's better to instead of having to write if else conditions matching the braces, it's better to maintain a structure which actually maps opening brace to closing brace. And that would be a map. So a map suggests something like this. Let me quickly write it. And of course the algorithm is and then the algorithm becomes simple. Like when you always have to map a closing brace to an opening brace. The structure which lets you do that is a stack. While traversing the string, opening braces with like we push opening braces to the top of the stack, and when we encounter a closing brace, we map it with the top of the stack. If it matches, we discard it. If it doesn't, otherwise, and continue. If it doesn't match, then of course string is not valid. And at the end of the input, string has this stack has to be empty, indicating that there are no orphan open braces. So let's write code for this. And this makes it a little more flexible. Consider if we have more types of more types of braces, like using say there is some code language which we are trying to parse that just maintains this. And while not strictly necessary, this is something which would make code more readable. Not map set character. Again, the age condition. Null technically could be valid. Empty string could be valid. So we won't deal with empty string, but single character string is by definition invalid. We don't have to worry about it. So technically null is the only null is the only uh, null becomes the only corner case over here, and we can simply let me my apologies, I am a little dyslexic about exception. Invalid. Yeah, it's not illegal input, it's invalid input exception. Oh, no. Illegal. Oh, okay. It's illegal argument exception. And again, like in production, we would be writing a proper error message, but not here. Now, if you are coming from languages, if you are coming from old school C or C++, length used to be length used to be a function which used to take a single pass. But that's not like in the most modern languages, store length has an attribute, so it's a constant time function. Now note that I am using capitalized uh, character like the boxed data type for character. That's in order to prevent prevent auto boxing and unboxing every time we look up the collection look up into these collections. And of course, so there is a the Java collection framework has contains a class for stack, but the documentation for stack says that that's there for that's there for demo purposes only, and a more complete implementation is actually is actually available in class tech. But for the sake of this problem, it doesn't matter. We can simply use a stack. Now, first check. Now we first check if it's an opening brace. I think I spelled this wrong. My apologies. Parenthesis. This means it's an opening brace. Open braces dot push current. This would mean it's a closing brace. continue, and at the end, so let's see. Hmm, yeah, that's a corner case. That's a corner case. If so that happens when we start. That happens when at like during traversal we get some valid string including empty string, and we encounter an orphan closing brace, which instead of so let's see how it works. Hmm. Yeah, so I think I know why the runtime performance is poor, uh, and memory performance is poor. This could simply be fixed if instead of calling this char at every point, we just cache this into uh, we just cache this into a two char array. So something like okay. So let's try this. Hmm, it's a little better. And let's play with this. Hmm, that's definitely bad. Hmm. Or the memory performance is also maybe a little worse because of these these private static variables. But again, these variables um, make the code a little more readable. So that's like I would kind of justify that trade-off at this point. Okay, moving on. Hmm. So heads of two sorted lists, and then you have to then merge the two lists into a single sorted list. So the way we solve this is, uh, again, traverse, since these are linked list, and the list node class is given over here. Uh, what we would do is uh, we would have two pointers, one traversing list, the first list, and the other traversing the second list. And when we compare the two pointers, we take the smaller element. We take the smaller element, append it to the result list, and we continue this process till at least one of the list exhausts. At which point we stop traversal, and we have the resultant list. Just for the sake of simply just for the sake of simplicity, uh, we can assume like a head, like a sentinel head node, sentinel, not as in sentinel as in classic algorithm terms, like algorithmic sentinel, which is the border element used in many data structures. We would use a sentinel node as head node of the resultant list, and then check. Now, the good thing about these being lists is, corner cases should get handled in this scheme itself. And since next by default is null, so it would by default be null. Uh, you could technically use like a sentinel value. By default, integer values are zero in Java. You could use a sentinel value, but that's not strictly necessary. But just in order for a reader, it's a good practice. So that's the lowest negative integer that can be stored in an integer, that can be stored in Java. This is a good practice. This is just a good practice which tells which obviously, which indicates to the reader of the code later down the line that this might be a sentinel node, and in the end we would be returning. It's not a method. There is still one border condition here. If both input lists end up being null, uh, then whether and if just so if both so the case where both lists have end up list one and list two both end up being null is handled in looping handled as a part of looping condition. But what happens if only first list is null? That's a corner condition which still needs to be explicitly handled. Hmm. But how do you take them off the original list? And one last step is now you don't necessarily have to make sure that the next element is null. That will be handled later when we look at the next element anyway. So let's see. Hmm. Okay. Correct. Correct. Yeah, basically we had the next list, and then then the other list is not exhausted. And now list one. So let's see. Uh, let's do it this way. And the add should take care of it. Maybe. Okay. Hmm. Okay. Some memory. I think caching extra variables. This hurts the memory utilization compared to other solutions. But if that makes the code cleaner and easier to read and cleaner to read, then that's a valid trade-off. Okay, and the next, let's move on. By the way, uh, just to go over complexity analysis of all these solutions in case of twosome. uh, we had we only had like one constant extra memory for not found, and possibly linear, possibly linear again. Like I wouldn't call it theta n, but I would call it O of n space complexity. uh, the difference between O and the like big O and theta is like when you say big theta, it is big O as well as big omega, and here the big omega is not a guarantee. Just in case you guys want me to explain complexity notations further, please let me know in comments or in Discord channel. Uh, so this and n is also known as linear. So this has linear space complexity and linear time complexity because we are traversing the array only once. Similarly, with valid parenthesis, we potentially have linear space complexity, uh, big O of n, not necessarily big theta, uh, and and but at the same time, time complexity is theta of n, linear but theta of n, and that's a guarantee because because it's because it's what is it called as I'm forgetting forgetting the name asymptotically, like it's hard it's impossible to establish a lower asymptotical like sublinear asymptotical lower bound for runtime. And similarly, in terms of merged list, so here in this case, we are still in this case we are using constant extra space. Just the new head node and like another reference which points to the current merge point, and and the time complexity is linear in terms of smaller of the two nodes, smaller of the two lists, because looping condition stops holding stops, or we exit the loop the moment the not the smaller the moment the first list gets consumed completely, gets merged completely, which means if we denote list one by the list one, like a asymptotical bound on list one, on length of list one by m and length of list two by n, asymptotical bound on complexity would be big O or big theta of m plus n. And that brings us to the end of today's stream. Again, this was my very first stream, so this is not necessarily my best work. I hope I improve in terms of content along with the as I move forward along this journey. Thanks for watching. If you liked if you like this like the content, please like and subscribe, and if you don't like it, please let me know in comments. Please feel free to join the Discord server and let me know and feel free to chime in on Discord channels as well. Thank you, and see you in the next episode.